Hello, everybody, and welcome to this public lecture. Today, I'm talking about the 5G, 5.5G, and 6G fundamentals. A couple of words about me. I've been active in the ICT field for more than 25 years. And I have been serving both as an academic player as well as an industry player. So in the industry, I've been at Nokia for about 15 years and around 10 years plus at Huawei, serving as a scientific director, chief technology officer, and also chief cybersecurity officer. As an academic, I'm currently with the University of New South Wales here in Australia. So I'd like to start from a panoramic view about the 5G adoption, and I'd like to introduce you the global landscape. So we may start from this slide, which reports the current assigned spectrum for 5G and the live and planned 5G launches. As you can see from this slide, that capture the situation at the end of last year, we had already more than 120 operators that have received spectrum across the 3 bands. So we talk about the low band for frequency below 1 gigahertz, mid band for frequency in the range between 1 to 6 gigahertz, and in the high band means that we are radiating at frequency above 6 gigahertz. So most of the frequency and the deployment of 5G is in the C band, which is around 3.5 gigahertz. Look at the planned operator launches by the different regions. We have that 5G is on in most of the places, as here in Australia, where we can already enjoy more than 300 megabit per second on your smartphone. So as we speak, we have more than 110 operators that have received the licenses and currently are offering 5G services. Equally important is to have a view on the number of connected subscribers, and this slide I've made by summarizing the contribution from the GSMA and the GSA, which are the association of the carriers and vendors, respectively. We can see that from 2020, end of last year, to 2025, we will shift from 234 million connections up to 1.8 billion connection, which is about 20% of the global penetration. As you see on this slide, most of the connections are in China, where we have about 86% of the user already connected to 5G services, and we are expecting about 45% of the population in China connected by 2025. If you look a little bit more in detail, still on China, as China is the largest market, we have that by 2025, the carriers will invest up to 210 billions, and 90% of those expenses are on 5G. But of course, if you look at the global 5G adoption, we have that it's not just about China. Actually, in the relative proportion, we have that the most adoption and penetration will be in North America, followed by Europe, and then Asia Pacific. And all these 3 regions will account for 90% of the 5G mobile connection forecast globally by 2025. Now, about the terminals availability, and the different form factors. As we speak, we have more than 700 announced devices and 431 devices commercially available now. And the distribution of terminal is represented on this pie chart. We have that most of the devices are smartphones, followed by the fixed wireless access customer premises equipment. And then we have also a number of other type of form factors, which are basically different type of models that are integrated over different platforms, including robotic platform and drone platforms. The band supported in the downlink, means by the network, are the C-band, millimeter wave. We are also now having in place the reforming at the 2.1 gigahertz, 700 megahertz, and the 2.5 gigahertz. The supported banded devices are pretty much the same. And I would like to add that if you look at the capability of the terminals and the coverage, we have a massive deployment of 5G in the C-band, but we will also have communication services at much lower frequency. And here I'm thinking of 700 megahertz or like 800, 900 megahertz here in Australia, which we allow us much larger area, and therefore bring coverage also to the rural areas and countryside. About the technology roadmap and what the 3GPP will make available as technical specification group is the following. So 5G was already completely specified by September 2019 in all its configurations. So it means the wireless interface completely defined, the new radio. Then the non-standalone architecture was completed back in 2018. And then end of 2019, we also had the system in its standalone architecture completely defined. So that basically is the release 15 of the 3GPP specification. And end of last year, we also completed the release 16. That means, in addition of supporting and enhancing the mobile broadband experience, we are also having a system capable of providing ultra reliable low latency communication services, and therefore support the industrial IoT. Both set of specification full meet the ITU requirements, which is about the vision we defined back in 2015. Beyond that, we will have the release 16 currently under specification, and release 16 will not only enhance the earlier features, but will also allow us to have access to massive machine type of communications and other type of services for the vertical sectors. Then after the 2022, we will start defining a new set of use cases, new use case categories, and the 6G work will start. We'll start in terms of study items, which are basically a summary of the potential technology consolidated on technical reports. And then we start the work items, which is about the specification work. We will then transpose those specifications to standards and launch the system by 2030. So how does the system architecture evolve? What are we expecting? And what is a 5G in practice? So today we are here. That is our 4G system. And in 3GPP denoted as option 1, we have a base station, long-term evolution, LTE, connect to an evolved packet core network. So the first step for us is to add a base station, the new radio, and allow the mobile phone in its non-standard configuration to enjoy services through the 4G communication channel, as well as add a user plane pipe through the new radio in the secondary bearer split, as the host signal still passes through the LTE system, which includes, of course, the security controls and way we are assuring security. For then, the system will evolve, and what we will have, it is an NNSA and standalone fusion. That means we will add, together with the evolved packet core, the 5G core network, and therefore we will have capability in place to support legacy terminals, as well as terminals capable of running a full new radio end-to-end protocol stack. Finally, the LTE will be refarmed, so all the frequency will go to the new radio, as well as all the services, and we will reach out ultimately the option 2, which is a fresh end-to-end system in its standalone configuration. And of course, the standalone configuration in some countries also the one that starts first, because the thinking here is to keep all the services and legacy terminals on an 4G system, and then overlay that with an end-to-end 5G infrastructure, which comes with the new radio and the 5G core in parallel. And the mobility between the two systems goes through an inter-system handover, as the only way for the system to communicate is through the core network. Maybe an important thing to consider is that ultimately from release 17 onwards, we will have also the possibility not only to access the communication 5G services through terrestrial networks or cellular networks, but also through satellites, with the introduction of the low Earth orbiting satellites, as well as geostationary Earth orbiting satellites, not only for the backhauling the system, which will mean basically to still have access through the new radio station and then pass the signal through the satellite to reach out the core network. Here we are talking about having the capabilities of immediately accessing the non-terrestrial network, which complements the coverage provided by the cellular system. Here you have an example of architecture configuration and how the system will look like. You see basically that the GNOBs, the base station, it does include the remote radio unit, which is nothing else that a transponder placed, transmitter and a receiver placed on a satellite platform. The transmission of the mobile phones, if you think of having a simple terminal, will be at 2 gigahertz in the S-band, but there will be also specific satellite terminals that will operate in the Ka band, which is basically in the 30 gigahertz in the uplink. So from the terminal to the satellite in the downlink will be 20 gigahertz. What are we expecting with the deployment of satellites? It is massive coverage. It's of course intended that the capacity and capability in terms of latency and throughput will be lower than the one you will enjoy through the cellular system, but still here we can see that we can achieve with the geosatellites a footprint from 200 to 3,500 kilometers, and with the LEO satellites we will be in the range from 100 to 1,000 kilometers, which is perfectly sufficient to cover all Australia, for example. Just a quick view of the supported features from what has been currently deployed, what's coming next year. and then what we will have in place after that. So starting from release 15 and 16, completely finalized, we have that the new radio already supports a band, the spectrum from 400 megahertz up to 52.6 gigahertz. It is a fundamental difference with respect to the 4G that we designed this system to operate in the sub 3 gigahertz. So the waveform is not designed to perform at higher frequency, and therefore we have introduced the new radio. And so the release 15 has fundamental characteristics. As I said, it is targeting to enhance the mobile broadband experience. It has a soft air interface support by default massive MIMO dynamic spectrum sharing Espinosa, completely specified. And then it has element of low latency, especially at the radio interface, supports network slicing end-to-end, although the run slicing, it will be completely specified in release 17. And also it comes along with a strong security posture, which further improves the security of the LTE system. So the baseline is already coming in release 15 and will then further enhanced in release 16 and 17, depending on the services the system will support. For example, release 16 will not only be based on a GPS receiver, but it will support a triangulation feature. The positioning accuracy will be improved down to 3 meters, further enhanced to 30 centimeters in release 17. And release 16 will be also capable of supporting vehicle 2X communication, and it is the system that will replace the GSMR. GSMR is expected to retire by 2030 globally, and it has been agreed that the future railway mobile communication system will be a 5G system release 16 and 17, meeting all critical and mission critical type of services and the corresponding requirement also for the railway mobile communication systems. Then with the release 17, the spectrum support will reach out 71 gigahertz. Here the features are targeted for critical Internet of Things, and it is exactly when we are also expecting the access provided not only by the base station cellular terrestrial network, but also the satellite. The MBMS will be also supported in this release, and the multi-access edge computing will be finally also integrated with the 5G core network within this particular release. Maybe one word about the exposure to radio frequency electromagnetic fields, since I'm constantly receiving a question about whether there is any kind of adverse health effects on human due to electromagnetic field exposure. And there are very clear conclusions drawn by the International Commission of Non-Ionizing Radiation Protection. They've recently published a guidelines that has been practically globally adopted. So the non-ionizing radiations go from 100 kilohertz up to 300 gigahertz, and practically what we have found that through a number of scientific study, epidemiological analysis, that there is no absolutely evidence of cancer, that this radiation within this frequency range would lead to cancer or any kind of adverse effects on humans, such as infertility, as you're having here, what we have registered is that the current only health effects that have been identified are nerve stimulations for frequency that go and reach out to the 10 megahertz, and some heating effects on our skin from frequencies, say, above 100 kilos. So to stay safe, it means basically to stay below overexposure, below these limits of exposure that are given in terms of both electromagnetic field and SAR, which means watts per kilogram, or even watts for a worker, say, the one professionally exposed. We have also limits, as you may see here, for the health. So the one temporary exposed, or the residential type of people, and the workers, we have both limits expressed in terms of watt per kilogram, that's our mass, or watts per square meter. So those are the limits below which we won't have any kind of effect. And practically the conclusions of the European Commission is exactly that following the existing recommendations, the deployment of the 5G will not have a negative effects on people's health. Here you have examples of antennas, macro cell, and radiating both in the C-band as well as in the millimeter wave, and also picocell indoor. You see the transmission power is very, very, very low, typical of system with small antennas. So the standard proposes and specify different type of architectures. This is about the CDU split, or the so-called RAN disaggregation. And the disaggregation of RAN consists of having a different type of implementations, or different type of implementation of the protocol stacks that could be aggregated into a CU, so a central unit or a distributed unit, and then say the low part of the physical layer can run on a remote radio unit. So the split allows us to orchestrate the different protocol stack depending on the capacity and the capability we're having in place to backhaul the access network. So if you consider the first option, where we centralize a part of the protocol stack, we have benefit that the resources can be shared, and the control plane as well over largest area. So this is particularly beneficial in the rural areas or countryside where there is very, very, very little traffic. When the traffic increases, we tend to collocate the CU and DU, which is practically today what happened all over the places. So we put them together so we can gain in terms of capacity and provide a better experience, especially in terms of latency. Then the standard also specify the integrated access and backhaul, which means the spectrum using for access I can also use to backhaul the access network. And you can see here how the system is specified by the 3GPP with introduction of new interfaces, and the interface between the donor node and the access node goes through the same interface as we are having here to access the system normally. So the benefit we see on the due to the split or RAN disaggregations are especially recognized for network slicing. Network slicing, it is a characteristic of 5G that comes along with the introduction of the 5G core network, and it is about composing, changing the service end-to-end virtually through the aggregation and communication of network slice instances. So here you have, you may see the different possibility. If I can virtualize, say, the CU stack, I may then decide clearly where to place it, depending on the service I am expected to deliver and the corresponding end user experience. So I will place the CU very close to the distributed unit, so the antenna system in the case of voice with high reliability, as well as I will do the same in the case of having in place platform that demand for very, very low latency, whereas when I have a little traffic and such as we're having here with the sensor devices or variables of any kind, I could think of centralizing the stack so achieve better efficiency of my communication system and the corresponding deployment. Yeah, now thinking of the potential services and having the possibility of enjoying the wireless interface, very, very, very high speeds. So we're thinking of 10 to 20 gigabit per second peak rates, latency below 10 milliseconds end to end, especially reduced when we think about deploying the services close to the edge of the network, which practically means close to the end user. We may think of achieving the so-called Cloud X configuration. So here you have an example of Cloud XR, where XR stands for augmented reality and virtual reality. So what we're having here, it is a system which runs services at the edge of the infrastructure. So let us have a look at this architecture. We are having here the end user devices like goggles that will allow us to have full immersive experience. They could be like augmented reality or virtual reality or mixed reality if you have elements of both experiences. Now, what we target here is to take out most of the functionalities currently, or would say in the past running in the end devices, and install them, run them at the edge cloud. And that would allow us to reduce dramatically the costs of the end user device on the one hand. On the other hand, is to reduce to reduce the cost of the devices, and on the other hand, have a better and user experience. So here you see that the capability, such as the interactions and the rendering, will be then moved to the edge cloud, where together with the interaction and server and the rendering server, we will have the possibility of running other type of applications such as AI functions. So this particular configuration will make it possible to offer services such as augmented and virtual reality at very, very low cost and reach out a marketplace, because we may think of that all those capabilities could be accessible and offered as a subscription to either the consumer or the vertical sector. So what the 5G makes possible is to achieve security, that is through the bearer service, which supports the primary authentication and the key agreement, which means practically encryption integrity using the 5G, And then we may think of expanding that with the introduction of the key for the application, for the authentication of the application function running on 5G. Practically, we have this feature coming with release 16, denoted as authentication and key management for applications. And beyond that, we will have the possibility of running as an overlay protocol, a secondary authentication with the possibility of encrypting data using a TSL and achieving integrity end-to-end of user plane using hash function, and then of course authenticating the end users and the corresponding application using OAuth 2.0. The architecture is currently further enhanced by the ORAN Alliance. So ORAN Alliance, it is an organization that runs in parallel through 3GPP. You see here, the proposal is currently to include more interfaces, so to further enhance the possibility of disaggregating the system and introduce new functionalities as well. And it is about the non-real-time radio intelligent controller for optimizing the performance of the system, say over minutes, hours, or even weeks. And the other function is the near real-time RAN intelligent controller, which will perform actions within much less delay. So here you have the interfaces specified by the 3GPP and a description of what comes with the ORAN Alliance. Now, going forward and think of 5.5G. So what we are expecting by 2025, currently we think of a system that will support 3 new usage scenarios. So the spectrum that we will have available, as I explained earlier, it is all the bands below 100 gigahertz, namely 72 gigahertz with 3GPP release 17. And the 3 new user scenario are basically the following. So first, the system will be able to support uplink-centric broadband communications, and that is in particular related to this manufacturing, the support of smart mining campuses, and so forth. We will also have the possibility of supporting real-time broadband communications, and that is basically applications like I have introduced earlier, as virtual reality, augmented reality, or say 5G much larger screen, such as 8K or even higher resolution. And the third new user scenario is about integrated communication and sensing, which, by the way, will be one of the main characteristics of 6G. Now, just to understand a little bit more about the new usage scenarios and use cases, I'd like to introduce you a bit more in detail what practically the uplink-centric broadband communications are. So on this slide, you have example of the different type of category of IoT connections, and you may see that the network deployment and the coverage requirements are different depending on the applications of the 5G system. So in the case of industrial IoT, we are thinking of a private network with very, very low latency and very high reliability of 5 nines and even more in latency, of course, below 20 milliseconds or even 5 milliseconds in specific cases. Then we have massive IoT, which require very large coverage areas, but they're also transmitting with the low power and very little traffic. Then we have the broadband IoT, and you may think of digital cameras, and then the critical IoT, it's all the elements that will be then integrated with the critical infrastructure. So the critical infrastructure, like here in Australia, it's not only a carrier network, but it could be a gas infrastructure transporting water, electricity, ports, and now we are also thinking of transport and the data center. The business, so we think of business to business, so we'll be an offering to the vertical sectors and the corresponding application we have today already available. The broadband IoT, as the system nicely supports speed above 100 megabit per second, and later, as the system evolves, we will be able to support also critical IoT and industrial IoT, demanding for much stringent requirements in terms of latency and reliability. So real-time broadband communications, it is especially about virtual reality and augmented reality that is expected really to explode in the next 2 to 3 years. So here you have an analysis made by the Gartner, where you may see that we are already enjoying, like in South Korea, we have a massive adoption of VR at 4K. So from TC onward, the system will be capable of supporting much higher resolutions thanks to the speed and capability of reducing latency. And beyond 2023, we think of an ideal type of experience as the system will run on average a throughput around 1 gigabit per second sustainable and latency below 10 milliseconds. So the shift we're having here is about moving from an handheld device, which all of us has one or two, to something that is rendered in the cloud and reproduced to the end user as an experience in terms of video. And that is particular what we target with the Cloud X solution I presented to you earlier. So practically what we have in place is the capabilities of supporting digital twins and different type of mixed reality with the possibility of applying this service to manufacturing, but also there are many applications on healthcare, and here this is also an example of retails coming along with the Microsoft. And looking at the operator and the possibility of monetizing as a business-to-business offering, what we are having is that right now we are basically here, and the monetization, especially with the consumers, but then later, as the capability of the system will evolve, we will have the possibility of offering the different type of services till achieving in 3 years, say, from now, virtual reality for socializing, and virtual reality also for the vertical industry, as I discussed earlier. About the integrated communication and sensing, this user scenario is extremely important, and it is about digitally connect the sky. the sky, we are thinking of different type of drone platforms with a number of possible use cases. So here you have some of those, and the standard requirements are about having capability in place to provide coverage up to around 300 meters, and the speed has to be above 50 megabit per second, with latency definitely below 50 milliseconds. That could be nicely, say, achieved with the release 16, and even better with release 17. So COTS intended, we need to have in place a proper regulatory and standardization framework so that our offering, so the running of an UAV platform supporting different type of services, it can be really come into market as it is properly regulated. Here you have an element of business dimension in terms of volume of connected drones, as well as targeted revenues from today to 2025. So we're thinking of more than, say, 73 billion business opportunity. Still, within the integrated communication and sensing, it's worth mentioning the vehicle to X communications, and the shift from we had back in the early 2000s till today, where cars where we know elements of autonomous functions, to what we are having today, which are basically, we have an assisted driving or partial autonomous driving, for then later by 2025 and 2030 reach out conditional type of automation. And finally, we will have an advanced automation, on even full automation, where we will let simply our car go and cross different junctions, as the traffic will be all shadowed by the network infrastructure with the head of roadside units and the communication vehicle to vehicle. As you see here, we have already on LTE the possibility of running vehicle to X communications. It will be further enhanced with the introduction of the new radio, for then, say, having it at scale. With the 5G supporting not only enhanced mobile band services, but also ultra reliable latest communication services and enhanced vehicle to X protocol. So the vision we're having of the network, in order to meet all these different types of requirements, is illustrated on this page. And by 2025, we are expecting to have a system in place which supports all possible service applications and all possible, or at least what we have identified as usage scenarios or scenario coverage. And in order to achieve and realize this vision, what we need to have in place are basically proper deployment criteria, so that we can enable business to business, business to customers, and business to home. We need to be able to support all spectrum. We must simplify the sites. Of course, the network architecture has to evolve accordingly, so that we reduce cost, at the same time meet all type of performance requirements. So in terms of supported services and the corresponding technical requirements, what we're having on this slide are examples of services that could be offered to consumer households, as well as to the vertical sectors. You see, today we have a system in place capable of running those services within the limit and constraints reported on this slide, and then to improve further the end user experience, or the B2B service, we need to further enhance the system to meet other type of performance requirements. For example, if you look at the connectivity to drones, today we reach out capabilities of 2K and 2D video with the possibility of going below 20 milliseconds in terms of latency and uplink speed of 25 megabit per second. But if we target to have a better experience, or even to capture with a drone the same type of resolution at a much higher height, it's much, to go up and have a larger footprint, then we need to support 8K, and 8K requires reduction of factor 2 in terms of latency, and then we have 4 times more speed. Coverage, basically, it is essential, and what we need to think of is a solution that exploit all possible bands. So the approach is to have a 1+1 configurations to also simplify the network. One is the central band, where the new radio will radiate. Typically, it is the C band, as we saw at the beginning of this presentation, and then we can complement that particular communication service in dual connectivity or carrier aggregation with the LTE, as the 5G requires a baseline and infrastructure of 4G on which, say, we create new services and new capabilities. So here you have examples of what we can achieve with a high bandwidth, and together with the other bands that could be, say, integrated based on demand. So if you think of coverage, that can be achieved to radiate in the sub 3 gigahertz, and that allows us to reach out rural areas. But as you can see here, as the frequency, carrier frequency reduces, also the possible transmission bandwidth is also reduced, and accordingly the end user experience deteriorates. So not all services are then possible to be delivered, but still we may enjoy, say, voice video calls, but it's very, very hard to have a very high resolution transmission that would require a higher carrier frequency, therefore the possibility of having a larger bandwidth, or at least I would say 100 megahertz band, so we can reach out and sustain around 100 megabit per second, which would allow us to enjoy a different type of service application. Then for local coverage capacity, especially in the dense Europe area, we may think of going up in frequency. In this case, we will have a transmission band, wireless band of 800 megahertz and even more, and therefore deliver an end user experience of gigabit per seconds. Yeah, the site has to be simplified for the sake of reducing costs and reduce also the pollution and also the time it requires for deploying the system. So today we are here. So all this cumbersome approach and configuration has to disappear. What we're thinking now is to have a super blade site, which is about bringing together all transmission frequencies on a single dish, and then use a combination of transmission antenna, that means the massive MIMO in the C band in the upper part of the radome, and integrate all other communication services in the low part, which means all sub 3 gigahertz transmission could be placed in here, and then the baseband unit can be also, the radio unit can be also consolidated, and the radio unit we can have dual and triple band, and also the battery, we may have a blade approach so that we can organize and orchestrate the energy among the different systems, therefore save a lot of electricity. Here you have examples of improvements. We may shift from a wake down to a day to install the complete site, and the total cost of ownership saving is in the range of 50% in terms of saving of energy, but also rental costs, because all this basically reduces to a single mast. Indoor deployment follow pretty much the same type of configurations. We have a very simple system. So you have Pico RRU, which are the radiating elements with the possibility also of beamforming, and that would allow us to achieve speeds even, as you see on this graph, of a gigabit per second, and the distributed massimo configuration, so the one you see here, using beamforming, can improve the capacity. So that means the number of accommodated end user at a given end user quality of a factor of 4. Yeah, the architecture by 2025 is expected to be consolidated, and it is well represented on this slide. So we have different type of accesses. We have a single connector, that the 5G connector. It is the first time that independent of the access, you may have a 2GPP type of access or known to GPP and trusted type of system. It doesn't matter. I mean, we have a unified way of authenticating, authorizing, and also the accountability has been unified. So here you have examples of a possible deployment. It is a system that has to support all possible scenario, multi-radio access technology. It is a fully distributed network, and supports on-demand elastic deployment, and in particular, it is an intelligent network with the capability of sensing and integrating sensing with communication services, and self-optimizing by placing the different functions across the different data center that where those particular network functions could be installed and yeah, embedded. The technical challenges we're having when we think of bringing or enhancing the system with artificial intelligence are pretty much captured on this slide. So what we want to have in place, in addition to the user plane, control plane, and management plane, now we would like to integrate the concept of the machine learning pipeline, which is an artificial intelligence closed loop way of achieving automation. And we discuss the possibility of having a federated learning. So the different type of source information can be then integrated to further enhance the model that are trained. We also think of improving the security controls so that the machine learning pipeline achieve a trustworthy system, resilient, but also preserving privacy. And on top, we are currently thinking of the installation of a number of AI-enabled applications that would practically complement the different services already in place. The system will integrate not only a network function orchestrator, but we are thinking of also a machine learning function orchestrator that would allow us to compose properly the different machine learning pipeline. And ultimately, what we are expecting here, that the machine learning functions will collaborate with machine reasoning functionalities as illustrated on this slide. So what basically, just as a summary, what my vision is that the artificial intelligence will meet, so artificial intelligence in terms of machine learning will definitely meet the machine reasoning, and that will happen at the age of the network. So all intelligence will be practically connected with a zero trust approach, and we will make use of the digital twinning and the connectivity between the intelligent part of the network will be through 5G, its enhancements, and therefore 6G. So why I've come out with this vision? This is basically because of the current trends. So first of all, what we're having is that artificial intelligence, it is very, very, very expensive. So this slide I've taken from the Italian Institute of Technologies made by the professor Roberto Cingolani and Giorgio Meta. So here you have the son of Roberto, and that is the, say, the humanoid, the son of Giorgio. So we can see from this slide easily that AI is really a cost inefficient. So it's really, really expensive. So if you give, for example, a chocolate having around 1,500 kilocalories to this boy, he can run and perform tasks for more than a week, where correspondingly iCub, this robotic platform, will only run for a couple of hours. This is because our brain pretty much, it is 40 watts. And this is what we need to, that's how much we consume, how much power we dissipate. And this robotic platform, it consumes much more energy, as you need to power on with at least 200 watts. So practically what we're having that the cost per operations are for 1,000 to 500,000 hours in machine than humans to perform the same type of tasks. So intelligence then therefore has to go away from the robotic platform and go to the edge for reducing the costs of the robotic platform, but also because we want to reduce latency. So we need to be below 10 milliseconds end to end. Machine learning has many flaws and limitations and biases. So we need to make use of the machine reasoning as well. And then digitalization and digital transformation is now a must, because we must improve the productivity and improve our efficiency and reduce the greenhouses gas emission. And finally, we need to shift from the Internet of Things to the Internet of Intelligence, and that needs to be done using a zero trust model, which practically means that any entity in communication, that could be a piece of software, it could be hardware, or it could be a human being, when they come into communication, they need to authenticate each other, they need to authorize each other, and then have elements of accountabilities in place. So what is 6G then? Why do we need 6G? Yeah, the shifting paradigm here from 5G, 5.5G to 6G is just about shifting from connecting anything and everything to connect intelligence. Therefore, we want to move from the Internet of Things of today, enhanced tomorrow, to the Internet of Intelligence. And I am defining intelligence are functions with the ability to represent knowledge, to process knowledge and make decisions. If any of these characteristics is missing, that particular element cannot be considered intelligent. So in order to realize this vision or shift in paradigm, we have five key and fundamental, I would say, enabling technology. The first thing, we need to shift from a system which is artificial intelligence enhanced, especially targeting the performance improvement as in 5G, to a system that's AI native, and AI has to be used also as a semantic communication channel, as we have already completely exploited the channel capacity that we have been studying for more than 60 years. Then we need to move from the information-centric to an uplink and downlink sensing network. And that is possible because 6G is expected to operate in the millimeter wave and the terahertz. As the wavelength reduces to around 10 micrometers, we have the possibility of receiving both in uplink and the downlink a clutter type of information and images with a very high level of accuracy that we can integrate with the communication services and create a new type of offering, including sensing as a service. Security has to be improved, definitely, because if you look at the security controls and assurance for 5G, what we have today is enhancements of the functionalities we specified already for 4G. And we need to go beyond that. So today, a 5G achieves privacy by concealing, since the very registration determiner, it's IMSI, so the International Mobile Subscriber Identity. We need to go beyond that and preserve privacy with much more robust algorithm using AI. Integrity is achieved through hash functions. That means we generate a message, digest, and what we are expecting next is to make the system much more robust. And here we are thinking of distributed ledger technology, and we are all familiar with the blockchain. Cryptography today is all based on a shared secret key, which is stored in the core network, in the SIM card, and through this key, we derive all other keys so that we can achieve an end-to-end cryptography across the 5G system. What we are expecting next then is to have in place a post-quantum cryptography, creating quantum-resistant ciphers that future quantum computers cannot crack. Of course, we do have now a chance to not only think of enhancing the security controls, but we can achieve security by design and design the system really meeting the supporting the zero trust model. About the access to the services, that's not going to be only cellular or anyway terrestrial, it's going to be also through satellites. And then the LEO will be the one especially exploited. As I said earlier, this capability will be possibly also made available in 5G release 17 and beyond, but it will be definitely a characteristic of 6G from day one. And the satellite, the LEO, will allow us to achieve latency really of 1 to 3 milliseconds. And that is possible because the satellite link, so if I want to put into communication people on this boat with the one enjoying virtual augmented reality somewhere else, the link through satellites is going to be shorter than a potential orthodromic surface distance covered by deploying fiber. And finally, we need to move from a generic bit pipe. So this is just a pipe of bits, connectivity, network. We need to shift from this network to something truly, really prosumer-centered, where the end user is not only a consumer, but it is also a prosumer, which means that it will generate content and not only consume text, videos, or audio, or any other type of haptic communications. So the vision we are having of 6G is represented on this slide. The target is to connect the physical world with the cyber world. Currently, we are thinking of introducing the new communications channels, so in the downlink, so from the system to the physical world, we are discussing about introducing a virtual augmented virtual reality channel, as the VR will be the way that the physical world will access the cyber world. Will have support from day one a tactile channel, especially carrying haptic feedback, and then inferencing parameters, so that we have a possibility of constantly improving the algorithm at different destination as the system learns from experience in terms of sensing capabilities and learning capabilities, which are basically the characteristics and the fundamental enabling technology of 6G. Here you have an example how the architecture looks like. We are thinking of the base stations in terms of neural edge, and the data center will become the so-called neural center. So you have a distributed machine learning pipeline whose communication we currently target to have in place quantum key distribution, which is also particularly valuable for the characteristics of connected intelligence. And by the way, this kind of architecture and the vision of connected intelligence, Manzalini and I already made that publicly available in 2015 when we published a famous research paper that described the horizon 2020 and beyond in terms of distributed operating system, which is nothing else than the distributed intelligence targeting the true digital society. I would say also the true digital economy and silver economy. So you see here, we had already identified the time all the fundamental enabling technology from sensing to the edge computing capability on a neural edge, and also we discussed the neural center in terms of functions, elements with capability of controlling the end-to-end system and orchestrating the different network function, as well as the components of the machine learning pipelines. Right, so 6G now is very hot, and massive investment in this direction have been already agreed in place. You can see here that US already invests massively, not only on studying a new enabling technology, but also on test beds, similar actions And initiatives are ongoing in Japan, South Korea, China, Finland. Finland, we have an important 6G flagship as it is in the UK with Professor Rahim Tafazzoli, and the European Union has already allocated 900 million over the 7 years, which is basically 200 million more than what we had when we designed the 5G communication system from 2013 to 2020. Australia is also extremely active, and it was of last week that the federal government has announced the Australian digital economy strategy of 1.2 billion investment, and a part of the budget is devoted to 5G and especially 6G security. So with that, my lecture concludes. I thank you so much for giving me this opportunity to share with you my vision, what I think are the fundamental enabling technologies are, and I hope we may stay in touch. Here you have a link to my public page on LinkedIn. You may find the recording of this video and other videos in my channel. In YouTube, please share your feedback, constructive feedback, so that we can integrate that while we are defining the use cases and usage scenario for improving the performance and characteristic of 5G. But especially now, it's time to define the vision of 6G. So I thank you so much, and goodbye.